and it's a great pleasure to be here. And let me start by apologizing for not giving this talk in French. Unfortunately, my French is horrible, so I can fill out some forms to some extent in French, but in fact, I had to fill out one for Gilles Lebeau, who I'm visiting this summer in Nice, and there's a part about how my French is, and so there I put down pas bon malheureusement. So this is supposedly whether I'm good enough to teach in French. So of course not. Also, Dietrich told me that I'm supposed to be giving a talk for algebraic geometers. So I don't know. Maybe it will be partly not so interesting in for microlocal analysts, but hopefully it will be. So. I mean, after all, I'm sort of a bit of an odd PDE person, I think, in some ways. So maybe it works out just fine. Okay. So I should say something about what is this Feynman propagator first. Clear. So the overall setup is that one wants to think about wave equations. So this box, I'm going to give an example in a second. This box G is going to be the wave operator. This is going to be on some manifold Mg. So here G, so M is a manifold, and G is supposed to be a symmetric. So it's basically an inner product pointwise, symmetric 2 cotensor. And the Lorentzian signature, so with signature, and now you get to argue what the signature is, but let's make it say 1, comma n minus 1. So n is the dimension. So whenever you have a manifold with a Lorentzian matrix, so this is to say Lorentzian matrix, you just get the wave operator on it. So this is just going to be the wave operator and functions for this talk. And so you can just write down an explicit formula. So explicitly in coordinates, box G is just, if you write your coordinates as, say, x1, xn, box G is just 1 over the square root of the absolute value of the determinant of G. So you think of G as an n by n matrix times, okay, you get to argue about signs here as well. So I'm going to write it like this, dxi times the square root of the determinant of G. So this determinant of G absolute value is just the volume form, or really density. And either Gij, so this is the dual matrix, so the inverse of the metric tensor, dxj. And this is the sort of usual, so here my convention is that dxi is, okay, this is going to be another I here, 1 over I times the usual derivative. So I write these straight D's because these are the things that are well behaved with respect to Fourier transforms. I like to have the I incorporated. Okay, and so this is a differential operator, right? And this is just a multiplication operator by Gij, written in this standard analytic notation, but probably not the ideal notation. Again, multiplication by this function, differentiation, and multiplication by a function. So that's the wave operator, and of course the canonical example is you look at Minkowski space. So in which case so this is just Rn is the underlying manifold, and the metric is just with this signature, say dxn squared minus dx1 squared plus dxn minus 1 squared, and so this is time, and so these things are space. Okay, and so what we want to do is to understand properties of the wave operator at the end of the day. So, okay, so typically one thinks of the wave operator as an evolution operator. This sort of implies that I don't necessarily want to do that. You think of it as an evolution operator. So that is to say, you have some initial Cauchy hypersurface. And let's call it S. So e.g. in this Minkowski setting, xn equals 0. In Minkowski, and then you want to solve the equation where, so the wave equation with initial data imposed on the initial hypersurface. So u at S equals, say, phi, so this is given, and the normal derivative, v of u at S equal to psi, again given, where v is some vector field normal to S. So the picture in Minkowski space is that these are my spatial variables. This is, so let's call this x prime, x prime. This is xn, so that's time. And this is my initial hypersurface S. So I impose data here. So this is the initial position. So so one thing that the wave equation is supposed to describe, this is of course just about the worst thing to think of that the wave equation describes, the motion of a membrane where phi is the displacement, I mean u is the displacement, and so the time derivative of u will be the velocity of the membrane at the point x, so which remembers both space and time. So this is a second order equation. So just like for a second order ODE, if you want to think about this as an evolution problem, very reasonable to give two initial conditions, the value and the first derivative at the initial place. Okay, so this is the usual formulation of the wave equation. And so locally always everything works fine. So locally we always have unique solutions. So locally, so S is supposed to be some embedded hypersurface. And so globally things work if the space-time M is globally hyperbolic. So you can say different ways what this means, but so roughly but this is saying that each time-like curve, so because you have this Lorentzian metric, so you can say, you can evaluate, if you have a, I don't know, W is some vector, tangent vector to M, you can evaluate G on WW. And so with my signs, so if positive, you call it W is time-like, equals to 0, like, or null. And if negative, space-like. Okay, and so for global solvability, what you need is that each, and so these two things are sometimes called causal. So in terms of this picture, this is the Minkowski picture. Like means going at 45-degree angles. So this is only 1 + 1 dimension, so there isn't too much one can draw. I mean, the board is 1 + 1 dimension. And time-like means going at an angle that's steeper than 45 degrees. Okay? And so what you want is each causal curve intersects S. So you have to be slightly more precise in a unique point. So basically, here's my causal curve, gamma, and it's supposed to intersect S in exactly one point. So so unique. So it does intersect and only in one point. Okay? And so under this hypothesis, you actually have global solutions. So this sort of thing relies a lot relies on something that's very reasonable if you like evolution equations I mean, especially with sort of extra properties of the wave operator. So it relies on two things, on both the evolutionary properties, of course, but even more strongly on the finite speed of propagation for waves. So what this says is that if I take a point here, so this is my point, let me write it as x prime comma t, and you want to understand what the solution is at this point, you just have to take the backward light cone from this point. So just go backward light rays, and the initial data here, so I don't know, that's where D, so it's the domain of dependence of x prime t. So the data here determine ux prime t. So it has this very unreasonable property that, in terms of a linear operator, that in order to know what the solution is here of the equation, all you have to know is the initial data in this small part. So if you want to think of a linear operator as some sort of I mean, this is acting on functions, so on some infinite dimensional vector space. If you want to think about, say, some sort of generalization of a matrix, this sort of property is extremely unreasonable, right? So you shouldn't be able to invert a matrix. We shouldn't be able to find what a block of the inverse of a matrix is by just knowing what the inverse of that block of the original operator is. Right? So this is a very unreasonable property in general, but it's true for the wave equation. So it's sort of nice, but it's not very, I don't know, functorial or something. Okay, so okay, so that's the basic solvability picture. Now it turns out. So okay, so let me first reinterpret this. So reinterpretation. So I used actually inverse, and I didn't write down anything that's being inverted. So so this is equivalent to really to a problem with actual inverses to an inhomogeneous PDE, which would be solve the equation like this. So now you have a non-zero right-hand side. So this is given. So I didn't say I'm going to write down. This is also can be thought of as the global hyperbolicity as equivalent to having a global time function. Of course, it's not unique. There are many global choices. So given, so I'm just going to write informally a t down. So this is where the support of f, so where f is non-zero, the closure thereof, is subset over t is positive, and want u, the support of u, to also be in t positive. So this is the forward problem. Forward or retarded problem. So of course this or the backward version, which is the advanced. I mean, you should say or and advanced version. So this is where t greater than equal to 0 gets replaced by t less than equal to 0. Okay, so so in this version, I can really say that what you're doing is you are writing u is equal to box G, and say the retarded one would be, say, R. So this is for retarded, forward, inverse of f. So really inverting the operator. So notice that, of course, the wave equation has a lot of solutions. After all, you can specify the initial data. So the wave operator, in other words, has a huge null space, a kernel. But none of this is going to have this property. None of the kernel is going to have the property that it's supported in t greater than or equal to 0. So this inversion is at least not an unreasonable thing to do. You're not inverting something that has a huge null space. It has a trivial null space, this operator. And then similarly, in this case, it would be a bug GA inverse F that you are looking at. So the one nice thing, so here I said t greater than or equal to 0, but maybe it's even better. Let's change it to some t0. T0 is anything. And you could even just say that instead of specifying t0 for, that there exists a t0 such that, blah, blah, blah. And then the surface itself doesn't really show up. So there's no Cauchy surface then. So Cauchy surfaces are, of course, very artificial. You don't see a Cauchy surface in real life, right? So they don't exist. I mean, you have to specify them artificially. This gives you a way of phrasing the problem without Cauchy hypersurfaces. So that's sort of nice. OK, so here we have then two inverses of the wave operator. Of course, what does inverse mean? That you're inverting this operator. I didn't actually write down precise function spaces, but it's an operator, so it's acting between two function spaces. So what you're really doing is you're inverting bugs G on different function spaces. OK, and then so then a reasonable question is, are these the only two sort of reasonable inverses? And so the answer is no. So there are other reasonable inverses.
But you have a global time?
Yes.
You assume that you have
Yes. I'm assuming global hyperbolicity. So there are other reasonable inverses. So because of this very unreasonable property of the wave equation, you really get away with no more assumptions for these two, which should be really unreasonable. You shouldn't be able to, like in an elliptic equation, like the Laplace's equation, you cannot just say that I'm going to solve this in the favorite subset of the set I'm going to care about and ignore everything else. It's not going to work. So that should be the model, right? I mean, the Laplace's equation is like, it's an elliptic operator. It's the best possible operator in the world. I mean, elliptic operators in general, like d bar, say, another very nice operator. So hard to beat. So that's sort of the standard. If it doesn't have a property, then it's not a very typical property for reasonable operators. OK. So for these sort of things, I need extra structure. So under some extra hypothesis. I mean, in some ways, philosophically, what's happening is that for these sort of equations, because of this finite propagation speed, when you can solve the problem locally in your space-time and then piece together solutions. And everything fits together nicely, and everything is great. So this means that you can ignore most of the world while you are working. And so this is fine for local theory. But even if you try to understand how solutions to the wave equation behave globally. So what happens when time is very large, for instance? This is not very good. And so what this corresponds to, in some philosophical sense, in finance, is just not worrying about the future, dealing with the immediate situation, and then just let whatever happen. And we know that it doesn't lead to very good outcomes. So we want to think globally. OK, so there are other reasonable inverses under extra hypothesis. And so these will turn out to be the Feynman and anti-Feynman propagators or inverses. So in Minkowski space, this is actually explicit. So this is, of course, Feynman in Minkowski space, who started using this for quantum field theory purposes. So in Minkowski space, what you can do is Fourier transform in space-time So you really take, your Rn, your space-time, has no automatic product decomposition. I mean, there's no canonical product decomposition. So Fourier transform in space-time, and then what you see is I code my variables xi, then what you get, wherever my wave operator is, I mean, there's the metric and so a corresponding wave operator. So you get something like the box G corresponds to a multiplication operator by psi n squared. So this is the dual to time minus all the other things. And so the inversion you do will be that you are adding or subtracting an I epsilon from this. And so what you're doing is the Feynman, well, I don't know whichever signs, inverses are so plus minus I0 inverse. So you're adding an I epsilon and then taking a limit in distributions as epsilon goes to 0, so with a bit of care. At 0. So the issue here is that this is the basic problem with wave equations, just straight wave equations, massless wave equations. So there's no like m squared term, a mass term to get a Klein-Gordon equation. Is that unfortunately they are a homogeneous quadratic object. So in this case, you have a multiplication by a homogeneous quadratic function. And so unfortunately, this implies that they have a quadratic 0 at 0. So this thing vanishes quadratically at the origin. So this sort of thing makes very nice sense as soon as you are away from 0. So the picture, I should draw the picture. So let me try to do a higher dimensional picture, which I, of course, very bad at. So this thing, this 45-degree cone, this is the light cone. So this is where psi n squared. So the light cone. So these correspond to the null. These are dual, so really cotangent vectors. So null vectors, null covectors. So that's the light cone. And so, of course, the cone, and of course, goes on the other way. The cone is perfectly nice and non-singular away from the origin. And so this thing makes perfectly good sense. But at the origin, it does not. So you have to work on trying to actually make sense of it. OK. So but away from the origin, everything is great. So OK. So at least in this case, you have an explicit formula. But if you go to any other setting, you're not going to have, well, maybe not any other setting. Apart from very few settings, you're not going to have an explicit formula. And so you would like to understand, you would like to have a framework for understanding Feynman propagators, what they actually do. And even here, you have an explicit formula, but it's very hard to see from an explicit formula what this actually does. Like, how does this differ from, in what ways does it differ from these causal propagators? So advanced and retarded propagators. And so that's what I will try to explain. So as I mentioned, all this has a lot of motivation. In particular, Feynman did this because of quantum field theory. So I'm not really going to give a talk on quantum field theory. And in fact, some of the people here, like Dietrich Hefner and Michael Rochna, would be much more qualified to do that. So you ask them for quantum field theory interpretations. What I want to do, in fact, let me listen one more thing, is that I'm perfectly happy to give this lecture here because some of these problems I started thinking about when I was here for the summer school 2 years ago, when Christian Gerard gave a series of lectures on quantum field theory. And in fact, he asked me about these positivity properties from this sort of solvability framework that I started thinking about at that point. So OK, so maybe I'm not going to give a QFT history. Again, the locals are much better at it. So let me just again emphasize Christian Gerard actually was the part of the motivation for working on this problem. So what I would like to do is to explain a framework. So how should one think? Of these different inverses. inverses when one cannot write them out explicitly. Okay, so that's the main thing I'd like to discuss. Okay, so I mean here, in some very hidden way, they really came from, the inverses came from considering function spaces on which the operator was acting. So here, for the retarded, we are thinking of functions that are supported, or distributions supporting t bigger than t0. And for the advanced, it's a sort of reverse inequality. So you may want to come up with some sort of generalizations of these spaces and have well-behaved problems. So let me say something about, so these are actual inverses of the operator on some function spaces. But one thing that we like doing in analysis is instead constructing approximate inverses. So let me say something about this. So parametrices. So these are approximate inverses. So what you want to, in this case, what you're doing is construct operators, let's say G, such that on some function space, you have that G is an inverse, in this case of, maybe you're interested in different operators, but right now let's just talk about the wave operator. G composed with the wave operator is almost the identity plus trivial, and also the same way the other way around. I mean, this way the trivial might be a different trivial. And so you get to decide what trivial means. And so the usual meaning of trivial is, so what's the simplest setting for analysis? The simplest setting is, OK, so in some ways you could say Rn, but Rn is actually not very simple. Even if you have, I mean, if you have translation invariant operators, then not so bad, you Fourier transform. But even then, this was not so obvious what to do. So Rn is not the simplest space. The simplest spaces are compact manifolds. And so on a compact manifold, the natural spaces, of course, there are two extreme spaces that are pretty good spaces. I mean, in terms of one of them being very good functions, the other one being finitely bad functions, namely C infinity functions. So we want to differentiate. We're solving differential equations, so we need derivatives. So C infinity functions on the one hand, and distributions, which are the dual space, so finitely bad objects on the other hand. And then there are some intermediate spaces, which would typically be, for analysis purposes, Sobolev spaces. So what this trivial should mean is regularizing. And then this depends on the setting. So now, on say, a compact manifold, what this would mean is map all distributions, or maybe distributions restricted to whatever subset you care about. So distributions, maybe with some extra conditions. Conditions to C infinity. So a different way to put it by the Schwarz kernel theorem is to have a C infinity Schwarz kernel. So it's really an integral operator with a C infinity Schwarz kernel. So, so this is fine on a compact manifold for one thing, because such operators are compact, for example, in any Sobolev space as operators from that space to itself, because they map into C infinity, and C infinity will include back into Sobolev space in a compact way. So you have something really trivial. Like if you have this, you have invertibility up to finite dimensional obstacles. You have a Fredholm theory. And so of course, this works very nice on a compact manifold, but in a non-compact manifold, you can declare the same thing to be trivial, but it's actually very far from trivial. So on a non-compact manifold, such operators are far from trivial. So let me, before actually saying where I really want to get with this right now, let me give an example of something that is trivial. So one non-compact manifold is Rn. On Rn, the thing would be trivial is Schwartz functions. So an example of something trivial is, so in Rn, so non-compact, you want trivial would be mapping tempered distributions, so the dual space of Schwartz functions, so basically roughly polynomially growing things, to Schwartz functions. So this means regularizing the sense of in derivatives and decay at infinity. And so these operators, again, on in this case, the actual Hilbert spaces, I mean, it's nice to have Hilbert spaces for analysis every now and then. So in terms of the actual Hilbert spaces, like weighted Sobolev spaces, they are actually compact operators. So again, they are trivial in this sense. So this is trivial. In some sense, if you have if M is a manifolded boundary, then in fact, there's a similar statement, so compact manifolded boundary. So there's a bit of argument you could make here what should really be trivial, but basically what you will want is sort of an analog of this, which would be the very nice object is what I will call C dot infinity, so this is Hörmander's notation. So this is vanishing to infinite order at the boundary. And what we'll call, I'm just going to call it C minus infinity for now, the dual space, so this is distributions. And so a map like this, so this is somehow tempered distributions, is trivial. So these are sort of trivial errors that you would like to get. Now, OK, so what you actually have in this setting, so it's going to be wave equations. So back to waves. So in a very impressive paper, Duistermaat and Hörmander, so this was the early 70s, like 71 or something like that, Hörmander constructed parametrices. So generalized inverses for actually even bigger class of problems, but let me just say for box G. So modulo smoothing in that sense. So modulo errors with C infinity Schwartz kernel. So smoothing operators like that. Moreover, they showed that there are OK, so maybe I should introduce a word here. So when you have a differential operator, so for example the wave operator, and in local coordinates you write it as P as some. So this is going to be the multi-index notation. So you write it like this. So this just means so d alpha is just d1 to the alpha 1. dn to the alpha n, just the various derivatives, and alpha is just a multi-index, where n is the non-negative integer, so 0 included. So you write the differential operator like that, and then the general philosophy in PDEs is that the highest order derivatives matter most. So you have a corresponding commutative object. So differential operators are non-commutative objects, and it's very nice to have commutative objects. So you go from non-commutative algebra, operator algebra to commutative algebra. So you want a function. And what this function is just, so I'm going to call it P, xc. What this function is that for each x, so here's x, you freeze the x, and you replace each of the derivatives by xi. And you only do this, however, for the leading order parts. And that turns out to be well defined. When it's, of course, obviously well defined like this, but this is actually well defined even on a manifold. If you use local coordinates, if c is here, you have to interpret it as a covector. OK, so that's the principal symbol of your differential operator. And so this is, I use differential operator, so this is actually homogeneous in xi of degree m. Now I didn't just write this down randomly. If I really think of x frozen, this is, and I think of this is a coordinate chart in Rn, I just have a translation invariant operator, and on the Fourier transform side, this is what it becomes. So this is just the corresponding Fourier multiplier. And so the operator is elliptic, p elliptic, if its little p never vanishes when xi is not 0. So it's homogeneous. It's going to vanish when xi is equal to 0, but you don't care about that. And so, in terms of Fourier multiplier, this means that you can invert it, take the reciprocal of it, so you can solve equations. And so if p is not elliptic, you will care about its, so these are easy. You care about the characteristic set, which is just the set where little p is equal to 0. So the inverse image of 0 under the symbol. And so what actually Duistermaat and Hörmander showed, in addition, is they constructed distinguished parametrices. So I will say why they are distinguished. Parametrices. And the way this goes is that you get, if sigma, the characteristic set, has k connected components, so characteristic of this wave operator, now this is going to be our p, has k connected components, there are 2 to the k distinguished parametrices. So what this means is that in each component of the characteristic set, you get to decide on something that takes values in a set with two elements, so like 0 and 1, or better yet, plus and minus. So so if you have a Lorentz manifold which is connected and time orientable, the characteristic set is going to have like Minkowski space. The characteristic set is going to have 2 connected components, and what this says is that you're going to get 2 to the 2, i.e. 4 distinguished parametrices. And so what these are is exactly parametrices 4. So they don't actually give you inverses, but they give you inverses up to trivial errors, which are not actually trivial. So what these are, so maybe write it here. Okay, so the inverses, or parametrices, the Duistermaat and Hörmander parametrices, distinguished, are the advanced, so it's backward in time, retarded, this is forward in time, Feynman, and anti-Feynman. So they constructed these modulo the smoothing errors. And they also write in the paper that they don't see how to fix the indeterminacy of these operators. So you can add any smooth Schwarz kernel and you get another parametrix. There are an awful lot of smooth Schwarz kernels on this non-compact manifold. So they don't see how to fix this. So in order to fix things, you actually have to really invert an operator. That's what will give you a fixed inverse. So you have to come up with some function spaces on which you are inverting things. Okay, so they also did another thing, which is a connection to quantum field theory. So that's where the positivity comes in. So they answered the question of Whiteman. Which was, are some of the differences of these, or can they be made? So, of course, so let's say, so the difference of this is a parametric, so I can't quite say that. Okay, so Whiteman's question was that do the differences, or can the differences, because they are parametrics, so they can only be defined up to adding smooth Schwarz kernels, and of course those can have any type of properties. Can the differences up to a factor of I, whose sign one has to decide on, I can't remember, be made positive operators? So in the sense of non-negative operators. So can you choose the parametrics so that they are positive? And so this was important for quantum field theory because of two-point functions that are supposed to have this property implications. And so what Duistermaat and Hörmander showed that in fact can be done. Okay, so that's the history. Now I should still explain. So why are these distinguished? So I already told you about the characteristic set, but what happens in the characteristic set? So in elliptic problems, you don't really get choices, right? So this says when you have an elliptic problem, you have 0 connected components of the characteristic set, and you get 2 to the 0, which is 1 parametrics. So you don't have any choices, but in non-elliptic problems, you have choices. And what does this correspond to? So so what happens is that there's extra structure here. So the cotangent bundle in general is, of course, a symplectic manifold. So it comes with a symplectic form. And so this can be used to turn vectors to covectors or vice versa. So it's a non-degenerate anti-symmetric bilinear form. And what this can be used to turn, so omega will map 1 forms. So it's really omega inverse, say, maps 1 forms to vector fields. So this is everything on T star m. So you have a 1 form on T star m, and out comes a vector field on T star m. And so this is relevant because we have a function on T star m, namely p, the little p. So little p is a function on T star m. And so you can take its exterior derivative, so now you get a 1 form on T star m, and then you can turn this into a vector field. So this is omega inverse. It's the Hamilton vector field. And then the dynamics that happens here. So this is tangent, is automatically tangent to the characteristic set. So the Hamilton vector field, you don't care about outside the characteristic. Outside the characteristic, the problem is elliptic and nothing can happen. So the only interesting place where anything can happen is the characteristic set, and HP is tangent to it. And then the integral curves of HP, so they inside sigma are called bicharacteristics or null bicharacteristics. And then Hörmander's theorem, which so it's a so-called positive commutator proof, and then Duistermaat and Hörmander gave a parametrics construction, which is a different proof. So Hörmander's theorem is that singularities of solutions of say pu is equal to 0 or pu equals to f, which is saying there's much better ways of saying things, but let me just say it like this way, propagate along by characteristics. So the picture is, so I'm going to draw a phase space picture. So the cotangent bundle is phase space, right, in physics. So x is position and psi is momentum, where x, in this case, is the space-time position, so space and time, and psi is the space-time momentum, so say momentum and frequency. Okay, so the picture would be, so the whole picture is sigma, and then I have these by characteristics. So this is the HP, so HP is like this, whatever. These are the integral curves. And what Hörmander's theorem is, so I have to explain the singularity. Hörmander's theorem is that, so the singularity, let me say this now. So this is actually the wavefront set of U. And so if U is a distribution, then you can get out of this a wavefront set. So that's going to be a set which is sitting inside the cotangent bundle minus the 0 section in this conic. And what it tells you is it measures if U is C infinity, so quote at a point in T star m, or near a point in T star m. So basically you're asking whether this distribution happens to be C infinity at a point in the base and in a certain co-direction psi. That's really what this statement is. Okay, and then the choices, the distinguished choices, correspond to in each component, connected component of sigma, get to decide in which direction. So there are only two directions, along HP or opposite, or backwards along HP. So forward or backward along HP. We propagate, say, regularity, so the opposite of singularity. Regularity or slash estimates, equivalent. So, okay, so it didn't say here what happened. So what Hörmander's theorem says is if U is nice at the point, so it has no wavefront set at the point, then U is nice, so it has no wavefront set at the whole by characteristic. That's Hörmander's theorem. So you can just propagate singularities or equivalently regularity along by characteristics for solutions. Okay, so the choices are, do you go along HP or opposite HP? And so if you go to the back to our Lorentzian setting, what this corresponds to, you have two connected components, and you can decide that in each you go, say, forward along the HP flow. So that's going to be the Feynman propagator. So, well, Feynman parametrix. So the Lorentzian world is that always forward is Feynman. Always backwards is the anti-Feynman. And then what happens is if you work out what this Hamilton flow does, I could just write down the Hamilton vector for it, it's super easy. What it does is, in terms of the underlying time function, is that in one characteristic, one component of the characteristic set, it goes forward as you, it increases as you go forward along the Hamilton flow, and the other one it goes backwards as decreases as you go forward along the Hamilton flow. So for the causal ones, parametrices go opposite directions in the two halves. of sigma. So based on this, it's clear what the good thing is, right? The good thing is be consistent. Go always forward or go always backwards. So that's in the Feynman and the anti-Feynman. Okay, so so I think I managed to explain what at least the Hörmander-Duistermaat theorem is without stating it explicitly as a theorem. So what's the so this gives you parametrices, which are all very nice. But what's missing is invertibility, or almost invertibility. So what you really want is to make what I call the trivial errors really trivial. So what you want is to make the trivial errors really trivial. So that is to say, in a concrete setting, so e.g. get decay at infinity in Rn. That's one way of putting things. Now, I'm not going to have time to actually do this, so I'm going to give you a toy version of the problem, but it's almost category theoretic. So all you have to do when you want to go to the actual wave equation, so I'm going to give you an example on a compact manifold. What happens in a compact manifold? That's all the actual interesting features. Going to this wave equation is probably some, there's some functor doing that. So what you're really doing is you're going from the tangent bundle, a cotangent bundle of a compact manifold to, there's a result. This is with the people I mentioned, so Gare-Redman, Haber, and Miha, is that there are, so if mg is modeled on, let me say it in slightly vague terms, but I mean it would just take too long to explain. You don't really gain much of it anyway. If mg is modeled on Minkowski space at infinity, so this doesn't quite mean that the metric is asymptotic to Minkowski metric. It's some generalization of that. It's sort of a generalization as saying that you generalize Euclidean space to spaces that are asymptotic to large ends of cones, Euclidean space being in particular a cone over a sphere. Okay, so modeled on Minkowski space, there are function spaces on which for each of these choices, there are function spaces for each distinguished choice on which box is Fredholm, so invertible up to finite rank obstacles. And in fact, there are actually invertible choices, but let me not say that. So let me say that. In fact, invertible. But the important thing is Fredholm. This is finite dimensional. Finite dimensional things are trivial somehow. So it's Fredholm, and the inverses you get with whatever choice you make, in particular, are this Duistermaat and Hörmander parametrices. So the parametrices are not unique, but in fact you get a uniqueness statement, and furthermore, the difference of the Feynman and anti-Feynman inverses up to a factor of I and the sign, whichever way you write it, is positive. And you can be further specify this, further refine this, so that's joint Miha to talk about 2-point functions, but I clearly don't have time to do that. You can have like 5 minutes to explain the. Okay, so this is the theorem, and I want to explain what happens in a compact manifold setting. So of course the wave equation. So this would say for the wave equation, the space-time is compact, so it's not very interesting. But every feature that's happening is already there for this compact manifold without boundary, no boundary. Compact manifold without boundary. Okay, so so the toy model on M, compact, no boundary. So the Minkowski, let me say one word what happens Minkowski, would be replace M by compact with boundary. So this would be a compactification of Rn called the radial compactification, so glue a sphere to infinity, and work with what Maros calls the B cotangent bundle, what algebraic geometers would call the real version of the log cotangent bundle. So this is boundary, so you can talk in the real world, you can talk about this. Okay, so that's the and everything. I mean, there's one slight twist, but it's not a huge twist. Okay, so let me explain what you need to do in a compact manifold setting. So what's the problem? So of course the elliptic problem is nothing happens and everything is great. And now you have this non-elliptic problem, and we have this very nice theorem of Hörmander. But what it says is that if a solution of a PDE is nice somewhere, then it's nice somewhere else. So it has a hypothesis. So somewhere you have to get the hypothesis. So where does the hypothesis in Hörmander's theorem come from? Well, if you have a really crazy bicharacteristic flow, it's not going to come from anywhere, so it's not going to be very good. So you want a structure to the flow. So you need structure to HP flow, and the structure is just that it goes from let me say it a bundle or maybe submanifold. So this is, remember, in the cotangent bundle, a submanifold, and in fact even better than that, you want to think about T star M. Remember that things like the wavefront set is I didn't say that, but I did say that, it's conic. So invariant under dilations. So this is not what you really want. For one thing, it's non-compact. So everything should be compact. Quotient out by dilations in the fibers. So this is the cosphere bundle. If you want the unit sphere bundle, but it's irrelevant. It's really just the quotient by dilations. It's just a transversal dilations. OK, so this is now a compact manifold. And what you want is that the HP flow goes from a submanifold of sources, so in the normal to the submanifold send, to a submanifold. So it's slightly more that you want, but let me say submanifold of sinks in a non-degenerate sense. It's slightly stronger than even that, but I think that's what I have time for. So the picture will be the following. Here's my sigma is going to look like, I'm going to draw it like curved. So I want to think of it as a torus, so it's going to actually go around in this way and go around in this way. So T2 on the picture. And I want to have something like, I'm going to call, I don't know, L plus, maybe L minus, to an L plus. So these are going to be my sources. This is my sink. And what I want is a flow that behaves like this. So it goes from L minus to L plus, and so something like this. And so connects up. So you want the flow like this. And so what happens is that there's a version of, so Hörmander's theorem at L plus and L minus is empty. It says nothing. So the Hamilton vector field in this homogeneous way just vanishes. It doesn't quite vanish in the normal, in the direction and quotient out, but which is important, but that's a non-degenerate part in some sense. But I guess I don't have time to say that. So Hörmander's theorem is vacuous at L plus minus, the sources and sinks. Okay, so however, there are theorems that have the flavor of Hörmander's theorem. And they are the flavor that there's a critical exponent, so critical regularity. Regularity, let's call it S0, such that if you take S bigger than S, so let's say S less than S0, so this is going to be my Sobolev order, so it's how many L2 derivatives I have. HS regularity in this wavefront set sense. So it's going to be a wavefront set relative to the Sobolev space rather than C infinity. Can be propagated into either one of these. So that is to say, if you have regularity, HS regularity, microlocally, so in phase space outside L minus, say, you can propagate it into it. But it has to be less than this threshold regularity. While if S is bigger than S0, now this is the really nice thing, then you get regularity for free. So if S is bigger than S0, regularity for free. HS regularity is free if one is a priori, but this is OK, in a space better than S1. Better than S0. So say you have U is in HS1 microlocally, where S1 is better than S0, implies that U is in HS. Where S can be a trillion, so much bigger than S1. And so this is what's enough. So free regularity, say here, which then propagates along, in this case, backward along the bicharacteristics to L minus, that gives you it gives you a mapping property statement. It implies a mapping property for the operator, for P. This is our operator when working on spaces, on function spaces of high regularity at one of these, at say L plus, say, and low regularity. So low, this is the relative to the threshold at L minus. Okay? And so this is exactly your choice. If you have this, when in each component of the characteristic set, you have such a picture of the flow, in each component you get to decide where you have the high regularity and where you have the low regularity, and you can propagate correspondingly. So say one example. Well, I'm saying an example. We also said in dynamical systems, of course, these sort of things played a major role in the recent work of For, Sjöstrand, and then Dyatlov and Guillermo. So, I mean, this has many applications beyond wave equations. So, example, a trivial operator, P multiplication by a function of a simple zero on a hypersurface. So let's call this, say, F. And so then, so say, let me just write it local coordinates. Say F equals x1 in local coordinates. Of course, in this case, the characteristic set is just the cotangent bundle over x1 equals 0 of the space. And then in this case, so you can, of course, inversion of P is just division by P, by F. That's the principal symbol. And you have these solutions, x plus minus I0 inverse, are, well, they satisfy P applied to this equal to 1. So this is in C infinity, of course. So they solve the PDE modulo C infinity. So you have these solutions. And this is exactly the critical regularity. If you are in a better regularity in this, then you're in fact in C infinity. If you're in a worse regularity in this, of course, you cannot conclude that you're any better than the regularity of this, because here it is, an example. So that's exactly the borderline. And so there's a systematic way of dealing with all this, and that's what gives you these Fredholm properties that give you the inverses at the end of the day. So thank you very much, and sorry for going over time.